Assalamualaikum. My name is Nuliana binti Abu Bakar. My metric number is J23A0553. So this slide shows the main component of the robocar in their function. At the front fork or ball pusher is used to push and control the soccer ball during operation. The wheel and motor system enables the robot to move and control its speed. The battery supply provides power to the entire robot system. The protective body or chassis support and protect the internal component from damage. Meanwhile, the wiring and electronic circuit connect all electronic parts and transfer signal through the system. Finally, the microcontroller board acts as the brain of the robocar. It executes program commands and control the robot movement automatically. So together, this component allow the robocar to operate efficiently and perform its intended robotic task.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Alif bin Azami. My metric number is J23A0703. This slide shows the introduction of our Robo Soccer prototype project. Advanced materials are used because they are lightweight, durable and suitable to robotic application. The prototype combines mechanical component, electronic and a control system to operate effective. This project also demonstrates how robotic technology can be applied to support modern industry developments.
This slide describes the material and method used to develop the robocar. Lightweight and durable acrylic was selected as the main structural material. Electronic components such as servo motor, wheels, a battery and a microcontroller were assembled to build the robotic system. After assembly, the prototype was programmed and tested to evaluate its movement, stability and overall performance. So this slide shows the material and component used in robotic car project. The acrylic chassis is used as the main body because it is lightweight and durable. Epoxy is applied to strengthen and secure the robot structure. Batteries and battery holder provide electrical power to the system, while the jumper, wires and crocodile clip are used for electrical connection. The microbit function as the main controller to program and control the robot movement. Servo motor and wheels help the robot move and perform its function. This slide explains the early method used in the robotic car project. First, the robocar design was created using SolidWorks software to ensure a stable structure. Next, epoxy resin and hardener were prepared and mixed with coloring agent. After that, the epoxy mixture was poured into a mold and left to harden to produce a lightweight and strong robot body. Explain the method used in the robotic car project. First, the epoxy material was tested using a tensile testing machine and SEM analysis to study its strength and surface structure. Next, the robot was programmed using Microsoft MacCode and controlled wirelessly through Bluetooth. Finally, all components were assembled onto the acrylic chassis and the robocar was tested to evaluate its movement, stability and overall performance.
Hello, Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Haikal Aizat bin Arifin. So today I will share our results and discussion regarding the tensile properties and structural integrity of our sample. So in this presentation, we will look at how this material behaves under mechanical force and connect those results to its physical structure. Our goal is to explain what the numbers are and tells more about the material's overall quality and strength. To test the structural integrity of the sample, we will be using UTM machine, Universal Testing Machine. We tested 3 different samples under the exact same conditions to keep our data accurate. Each sample had a starting length of 100 millimeters. We pulled them at a steady speed of 20 millimeters per minute using a tiny starting force or pretension of 5 newtons just to keep the sample straight before the real test began. So this setup ensures our testing is fair and reliable. Let's take a look at the graph showing force versus elongation, which simply measures how hard we pull versus how far the material stretch. Looking at the lines, we can see two very different behaviors. Test 1 and Test 2, shown by the red and blue lines, followed almost the exact same path. They were able to hold a much higher force but broke earlier, around 87 millimeters. On the other hand, Test 3, shown by the green line, behaved differently. It could not hold as much force, but it stretched much further, reaching over 108 millimeters before breaking. This tells us right away that different parts of the material do not behave exactly the same way. Let's dive into the specific numbers to understand this better. On average, the peak force the material could handle was 175.5 newtons. The average peak stress, which is the force spread across the thickness of the sample, was 3.5 newtons per square millimeter. The most important number here is the Young's modulus, which averaged around 3.51 newtons per square millimeter. In simple terms, a low Young's modulus means the material is highly flexible and stretchy rather than stiff or rigid. However, we also notice a high statistical variation in the peak force, which sits at about 26%. This high variation confirms that the material is not completely uniform throughout the entire batch. Let's connect these mechanical numbers to the material's surface microstructure and structural integrity. Because the material stretches so much, averaging nearly 95% elongation, we can conclude that its internal structure consists of highly flexible rubber-like chains that easily slide and unfold when pulled. But why did the test 3 break at a lower force while stretching further? When we look at structural integrity, the surface of a material is highly critical. Test 3 likely had a microscopic imperfections, tiny air pockets, or small surface variation on its skin. These tiny defects act as a weak spots. They caused the sample to yield early at just 123 newtons, but because the rest of the material was still healthy, it kept stretching out like a rubber band. In conclusion, while the sample has excellent flexibility, we need to improve our manufacturing process to eliminate the surface defects and ensure uniform strength across all samples. Thank you. To conclude our presentation, we have successfully developed a smart and efficient RoboSoccer prototype. By combining modern materials technology with mechanical, electronic, and control systems, our team created a fully functional robot design for industrial and automation needs. A major success of this project was our material selection. Using a lightweight Arclic chassis paired with custom-made molded epoxy resin gave our robot a highly durable protective body. This ensured excellent structural integrity while keeping the vehicle fast and lightweight. Furthermore, all components from the microbit microcontroller and servo motors to the custom ball pusher integrated seamlessly. The systems successfully executed program movement and handled the soccer balls with great stability. Ultimately, this project proves that using advanced, lightweight materials is key to building the next generation of efficient, smart robotic technology. Thank you for your time.
This video showcased the Sulam activity where students actively participate in the RoboCar project from design and assembly to testing, while sharing knowledge with their peers.